And the cases that we studied, it was quite easy to see why a given series was convergent or divergent, mainly because either the terms that we added up did not converge to zero, or because we could compute an explicit formula for the kth partial sum. In general, this is not quite as easy, and one needs to develop tests to decide whether a given series is convergent or divergent. And I think the best or the most useful test for you in the context of probabilistic models is the so-called integral test from section 9.3. It's not very difficult to do. And the main question that it concerns is the following one, which is that we know that a harmonic series is divergent, and what we were interested in is what happens with the series that we get if we do not add up terms 1 over n, but 1 over n to some power p, with p bigger than 1, for instance. And what happens in that case? Is it divergent or is it convergent? And this integral test is extremely suitable for checking convergence and divergence of this series. Now let me formulate the integral test. It is theorem 8 from section 9.3. And it states the following result. So let us be given a sequence of numbers an, but these an's are in fact equal to a given function f evaluated at the point n. And for some function f, and we have to require some properties for this function f, namely the following ones: that f of x is non-negative for x non-negative, and what is even more important is that fx is non-increasing, well, starting from some large number n. So this f has the following form. It may be a little bit weird for small values of x, so it may go up and down, but after some time it will start to decrease to 0 because it's non-negative. Say we have our number big N over here. Okay, what is the result of the theorem? That the series and the following integral, the improper integral of x f over the interval from n to infinity, that both these things are either convergent or divergent. So if we want to know something about the convergence of this series, we only have to check the convergence of the improper integral, and that is often much more easy. And we will see this from the example of an being equal to 1 over n squared. Okay, are we in the situation of the integral test? Yes, because an is equal to a function f applied to the point n if we take the function f of x equal to 1 over x squared. Now, does the function f equal to 1 over x squared satisfy the conditions of the theorem? Yes, because it's non-negative, and 1 over x squared, well, you know that 1 over x squared converges to 0 for x tending to infinity. It's non-increasing for all x greater or equal to 1. So okay, so we have that the conditions of the theorem are satisfied, and so the conclusion is that the series and the improper integral converge or diverge together. And so we will check what happens with this integral. So this is a very nice test. But let us check what happens with this integral. Now we compute the integral of our function f, which is equal to the integral of the interval 1 to infinity of the function 1 over x squared. And we know that this is an improper integral, so formally we have to consider it as a limit over the interval 1 up to r when r tends to infinity. So okay, we can replace f of x by 1 over x squared. And if we look at the primitive of the function 1 over x squared, this is equal to 1 minus 1 over x. We have to evaluate it between the boundaries 1 and r, and we have to take the limit for r tending to infinity of this expression, and this is equal to minus 1 over r minus 1 over 1, and we see that this is equal to 1. Okay, so this is a convergent integral, and so the conclusion is easy, that the series is convergent. And there are other methods to tell us what precisely the sum is, namely the sum is equal to pi squared divided by 6. So if we divide by pi squared over 6, then 6 over pi squared multiplied by this infinite sum is equal to 1, and so if x is a random variable with probability that x is equal to n is equal to 6 over pi squared multiplied by 1 over n squared, then this is a nice probability distribution. And if we consider this probability in distribution and compute the expected value of x, then this is equal to, well, x takes the value n with probability 6 over pi squared multiplied by 1 over n squared. And what you then see, and that's why I gave the example, that this one term n in the numerator cancels one of the factors of n squared in the denominator, so we get in fact a harmonic series, and this is divergent. So this means that the expected value of x is not finite, so x doesn't have a finite moment. And this is a very nice example of a random variable which has a non-finite expectation.